A couple of weeks ago, I stumbled upon this special controller made by Microsoft called the Adaptive Controller. And it's made for disabled gamers. It's designed to be very modular and flexible to people's different needs. However, it is extremely expensive and very large and bulky and has a lot of separated components. So I thought maybe I could make a smaller, wireless, and significantly cheaper version of this. So my goal with this project was to turn this iconic two-handed, two-joystick, four-button controller into a one-handed controller without compromising on the range of inputs that was available to the user. I started out by just making a simple 6-button, one-joystick controller. For the brains of the controller, I'm using this ESP32 microcontroller, and it's what's basically taking in all the button inputs, and it's where all my code goes, and it's how it communicates to the computer. I chose this particular one because it also had the capability of using Wi-Fi and Bluetooth. And after cleaning up the messy wiring a little bit, I finally had an actual controller. So as you can see, this is communicating with the computer over Bluetooth. As I move the joysticks and push the buttons, they map and light up successfully on the screen, which tells me everything's working great here. Now the single joystick and 4 buttons can be controlled with one hand, but the added challenge was, how do we add the other joystick and still control it successfully with just one hand? To accomplish this, I'm using an IMU, or Inertial Measurement Unit, and it's a special chip that combines 3 sensors, an accelerometer, a gyroscope, and a magnetometer. And it combines them so that it can tell orientation, acceleration in 3 different axes, rotational velocity, and the magnetic field around it so it can tell which way is up and down. Getting good readings from this chip onto my particular board was quite a challenge because I had to write my own library, and the IMU involves a lot of complex math and requires very good calibration in order to give accurate readings. So here's a quick demo of the MPU library. So right now, if you look at the acceleration code, you see that the X, Y, and Z, the Z is about approximately 1, which makes sense because if you think of it, the axis is oriented like this, so the Z is pointing towards gravity. But if I flip it over, right, now the Z is, if I get it perfectly flipped, there you go. Z is at -1 approximately, because the Z will be pointing in the opposite direction to gravity. And if you notice, the X and the Y are approximately 0. Right now, if it's a little off, it's because I can't get it perfectly perpendicular. But since the X and the Y are perpendicular to gravity, it's going to be approximately 0. And then if I instead flip it forward, you can see that the Y value is now +1, because now it's pointing towards gravity. Then we flip it back. I can flip it this way. So now the X is a +1, and because it's going to be parallel in the direction of gravity. The orientation data from the IMU is accurate enough where I can make simple apps like this, where I control the direction of the plane using just the board. So if I was able to incorporate it into my controller, I could use the movement of the controller itself in the 4 directions as its own joystick. With this successful prototype, it was time to make the actual controller more compact. I threw the joystick, microprocessor, and IMU onto a single board and wired everything up as it had been before. I went through a couple of prototypes for what the buttons should look like, but eventually picked up these cool LED buttons that not only looked cool on the controller, but also made it easier to tell the buttons apart. I wired the LEDs on the buttons so that they'd turn off as the button was being pushed. I hooked all the buttons up to their respective digital pins, except for the green button, which I also wired directly to power. You'll see why in a second. Once everything was wired up, here's what the controller looked like. To make everything more compact, I'm going to be powering this whole system with a small LiPo battery that connects directly to the microcontroller. Now here's where that decision to wire the green button differently comes in. Since it's hooked up directly to power, it turns on when the controller is on, and then the other buttons turn on when the controller is ready to go. Once everything was hooked up, I give it one final test. The bars on the top right correlate to the X and Y rotation of the controller, which simulated a virtual joystick, while the plot on the left is the X and Y movement of the actual joystick. And as usual, the circles on the bottom light up as the corresponding button is pushed on the controller. As you can see, despite the fact that the enormous amount of movement and orientation data is being transmitted wirelessly, it's all very fluid, fast, and in real time. This was actually one of the biggest challenges of this project, and I had to write my own library and really learn the Bluetooth protocol in order to pull this off. Here I took apart an old PS3 controller and I'm using its shell as a more comfortable base for my controller. I would have loved to demo the controller in an actual video game, but unfortunately my PC didn't have any joystick compatible games. So instead, here's a program that maps the movement of the joystick to an Xbox 360 controller so you can get an idea of how they correlate. So you can see when I tilt the controller left and right, it's correlating with the movement of the left joystick, and when I move the right joystick, that's correlating to the movement of the right joystick. So I'm emulating both with just this one-handed controller.